have to discuss about spontaneous process and non-spontaneous process. What is the spontaneous process? What is the non-spontaneous process? So first one, spontaneous process. Spontaneous process means the process occurs naturally. The process occurs naturally, whether it's own or any initiation after it occurs. Initiation means just stimulating. Any initiator we have to use. So generally, maximum natural process occurs itself. Simply, spontaneous process means naturally itself takes place. Some process are we have to use initiator, after that it's occurs. That is spontaneous process. So examples: water flow from high region to low region, high to low. Second one, heat transfer from hot body to cold body, hot body to cold body. Next, pressure move from, or diffusion from, high region to low region, high to lower. All these processes are naturally occurring. Okay, these processes occurring itself or its own takes place. That is called spontaneous process. Naturally occurring itself. That is called spontaneous process. Some process, if we use initiator, they are also naturally occurring. Examples: fuel. Some fuels okay, for example, methane. If you use oxygen used as a initiator, it gives rise CO2 plus 2H2O. Then coal. So if you use oxygen initiator, it gives CO2. So these are the fuels. So these also we consider as a spontaneous process. Okay, that means some process takes place naturally its own. Some process takes place by using of initiators. After that they can occur. Next, non-spontaneous means we know it. Non-spontaneous process. Right. Non-spontaneous process means this process does not occur its own. So this process does not occur its own. We have to use some external force. From outside. So does not occur its own This is about the non-spontaneous process. Non-spontaneous process. Next one. Okay. Next one. Criteria for spontaneous process. Criteria for spontaneous process. Very, very important. Okay. What is the criteria for spontaneous process? Minimum energy, more stability. Minimum energy, more stability. This is important. Minimum energy and more stability. More stability. Next one. Second one, more randomness. Randomness means not properly ordered. Jigsaw. Okay, not regularly ordered. Randomness. So, more randomness. More randomness. Randomness means disorder. Randomness means disorder. Disorder. Okay, this is the criteria for spontaneous process. Next one about entropy. 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 Yes. Entropy. Okay. Entropy is the state function. It is extensive property. Entropy is the state function. State function. It is extensive property. Extensive property. So what is entropy? Entropy is the measurement of disorderness of the system or randomness of the system. Entropy can measure disorderness of the system or randomness of the system. So it can measure disorderness of the system, disorderness of the system, disorderness of the system or randomness of the system, randomness of the system, randomness of the system. Okay, that's why entropy directly proportional to randomness, jigsaw moment. So entropy directly proportional to randomness. Okay, this is about entropy introduction. Then mathematical expression for entropy. What is mathematical expression? Entropy equal to, or yes, no problem. Entropy equal to heat observed by the system in reversible manner at temperature T. Heat observed by the system in reversible manner at temperature T. That's why entropy equal to Q reversible by T. Okay, this is also called the change in entropy. No problem. Del S means change in entropy. Q reversible by T. Both are correct. particular T temperature at constant at system in reversible manner at temperature T. Temperature T. The T means temperature. Already you know. T means temperature. So entropy equal to Q reversible by T. Okay. Next. Now we have to discuss formulas one by one. First one, entropy in reversible isothermal process. Entropy in reversible isothermal process. Reversible isothermal process. Entropy in reversible isothermal process. Isothermal process means T2 equal to T1 because del T equal to 0. Temperature equal to constant isothermal process means. That's why temperature equal to constant means T2 equal to T1. Now formula del S equal to N or ln V2 by V1 or same formula del S equal to, instead of ln we take log. Ln equal to 2.2303 log. Del S equal to 2.2303 N or log V2 by V1. V2 by V1. Here V2 means final value, V1 means initial value, N means number of moles, R means real gas constant. Already knows. Real gas constant units depends on that particular case or particular sum. Okay, N means number of moles, R means real gas constant. So this is in terms of volume. So in terms of pressure, same formula in isothermal only. Next, entropy in reversible isothermal only in terms of pressure. Already we know pressure inversely proportional to volume according to Boyle's law. That's why entropy change equal to N or ln P1 by P2. Ln P1 by P2 or del S equal to in log 2.2303 N or log P1 by P2. This is in terms of pressure because pressure and volume both are inversely proportional. N not come amma. N are only coming. Temperature isothermal remains constant now. So only N are come. This is entropy reversible isothermal process. Next. Entropy reversible isochoric process. Reversible in isochoric process. Isochoric process means V2 equal to V1. Volume remains constant. That time formula del S equal to NCV. CV means molar heat capacity at constant value. CV means molar heat capacity at constant value. NCV. Otherwise, write to become NCV ln T2 by T1. T2 by T1. Yes, CV means molar heat capacity at constant volume. At constant volume. Then in logarithm del S equal to 2.2303 NCV log 10 T2 by T1. T2 by T1. This is a isochloric process. Isochloric process. Next one. Isobaric process. Entropy irreversible. Isobaric process. Isobaric process. Okay, isobaric process means P1 equal to P2 or P2 equal to P1. Okay, in this case, del S equal to NCP ln T2 by T1. Yes, Cp means molar heat capacity at constant pressure. Cp means molar heat capacity at constant pressure. So lambda converts to log del S equal to 2.2303 NCP log 10 T2 by T1. Okay, this is the entropy reversible isobaric process. Reversible isobaric process. Okay, so total formula, mixing formula, entropy in reversible change, entropy in reversible change, not made up, just to idea, total formula, entropy in reversible change, NCV ln T2 by T1 plus NR ln V2 by V1. This is total formula. Okay, otherwise NCP ln T2 by T1 plus NR ln T1 by T2. This is main formula. Okay, if isothermal means T2 by T1 constant. This term eliminated, this we use. Isothermal means temperature remains constant. This term remove, we can use this formula only, this part only. If isobaric means this part eliminated, this part only we have to use. Isobaric means this part eliminated, this part only we have to use. This is the main formula. Okay, next one. Adiabatic process, entropy in adiabatic process. Entropy in adiabatic process. Adiabatic process. Adiabatic process means Q equal to 0. You know, heat energy exchange is 0. Del S equal to Q by T. Here Q equal to 0 means here Q equal to 0 adiabatic. That's why del S equal to 0. That means in adiabatic process entropy change equal to 0. In adiabatic process entropy change equal to 0. Should remember now. Entropy change equal to 0. In which process? Adiabatic process. Next one. Enthalpy of vaporization. Very, very important formula, Sama. Enthalpy of enthalpy of vaporization. Enthalpy of vaporization. Vaporization means liquid converts to gas. Vaporization means liquid converts to gas. In this, del S equal to, del H means enthalpy change of vaporization. Enthalpy change in vaporization by temperature. The temperature means boiling point. Temperature means boiling point, because vaporization means liquid converts to gas. Liquids converts to gas means boiling only now. That's why liquid converts to gas means the temperature we should consider as a boiling point. So entropy change equal to enthalpy of vaporization by temperature considered as a boiling point. So del S equal to del H by T. Del S equal to del H by T. Next one. Enthalpy of fusion. 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 Fusion means melting. Fusion means melting. Melting. What is the melting, solid converts to liquid. Solid converts to liquid. Solid converts to liquid. Fusion means melting. Solid converts to liquid. Entropy change equal to, del S means entropy change. Entropy change equal to enthalpy of fusion. Enthalpy of fusion by temperature. Here temperature means melting point. Temperature means nothing but melting point. Melting point. So entropy change equal to enthalpy of fusion by temperature. Temperature means melting point. Okay. Next one. Next one. Enthalpy of sublimation. Enthalpy of sublimation. Enthalpy of sublimation. Sublimation means solid directly converts to gas, vapors. Sublimation means solid directly converts to gas. So entropy change, del S. Del S means entropy change. Entropy change equal to enthalpy change of sublimation. Enthalpy change of sublimation by temperature. Temperature means here sublimation point. So this is the three formulas are very important, especially enthalpy of vaporization, enthalpy of fusion is very important formulas, very important formulas. Sublimation also third formula. Simple one. In these three cases, you should take directly entropy change equal to enthalpy change by temperature. They only mention whether vaporization, sublimation, fusion, they only mention in sums. Simple you take entropy change equal to enthalpy change by temperature. Okay, this is the another thing. Next one. For chemical reaction, okay, for chemical reaction, listen, A to B, right. Entropy change del S equal to entropy of products minus entropy of reactant. That means change in entropy equal to entropy of final minus entropy of initial. Entropy of final minus entropy of initial. So for reaction summa already we discussed del n equal to 0. Del n equal to 0 means del n means number of moles of product minus number of moles of reactant. Already we discussed in relation between enthalpy and internal energy. Del H equal to del U plus del N naught T. So here del N means change in moles of product minus reactant. If del N equal to 0 means entropy change equal to 0. If del N equal to greater than 0, if del N equal to greater than 0, entropy change equal to positive. If del N less than 0, del N less than 0 means reactant molecule, number of reactant molecules more than product. Del N greater than 0 means number of moles of product more than number of moles of reactant. Okay, in this case del S equal to negative. Del S equal to negative. This is the in chemical reactions. Del N you have to find out, del N you have to find out. If number of moles of product equal to number of moles of reactant means del N equal to 0, entropy equal to 0. If number of moles of product more than number of moles of reactant, del N greater than 0, del S equal to positive. If number of moles of reactant more than number of moles of product, del N less than 0, del S equal to negative. Okay, next point. Entropy explains randomness of the system is said. Okay, the important point entropy increases solids to liquids, liquids to gases, solids to liquids, liquids to gases. Entropy increases. Entropy increases. Entropy increases. Due to why increases? Solids to liquid, liquids to gases. Why entropy increases means solid means particles are very rigid, come close. That's why orderness is more. Liquid means little bit one particle away from another particle, weak binding. That's why liquid some disorderness is there. Gas means all particles disorderly arrangement. Between particles attractions are very less. That's why solid to liquid, liquid to gases, disorderness increases between particles arrangement. Otherwise randomness increases. So disorderness increases. Disorderness increases. Disorderness increases. That's why solid to liquid, liquids to gases, entropy increases. What is the reason? From solids to liquid, liquid to gases, disorderness and randomness of the between particles arrangement increases. Okay, this is next point. Next, this application is very important. Number of gaseous molecules increases, entropy increases. Number of gaseous molecules increases, entropy increases. Number of gaseous molecules increases. Number of gaseous molecules increases, entropy increases. Okay, CO2 more than O2. Okay, CO2 gaseous molecules. Otherwise, this is atoms. Some examples we take any gas form, SO2, SO4, whatever it is. So gaseous molecules combination of gas molecules increases means so entropy increases. Next point, temperature increases, entropy increases. This point important. Temperature increases, entropy increases. Okay, for example, Fe, same Fe, here 200 Kelvin, here 300 Kelvin. So here to here, entropy increases. Because temperature increases. So simple remember, whether solids, liquid or gases, whatever it is, if temperature increases, entropy increases. Third one, pressure decreases, entropy increases. Pressure decreases, entropy increases. For example, nitrogen, 3 atmosphere, equilibrium, and again nitrogen, 2 atmosphere. So left to right, entropy increases. Here, entropy increases. So simple remember, in any state of the compounds, whether solids, liquids and gases, temperature increases means entropy increases. Pressure decreases means entropy increases. Number of gas molecules increases means entropy increases. Randomness or disorderliness increases means entropy increases. Okay, then some examples. Graphite more entropy than diamond. Because in graphite what happening, disorderness more. Disorderness more than diamond. Okay, in graphite disorderness more than diamond. Next, denaturation of egg. Denaturation of egg, entropy increases. So for denaturation of egg, entropy increases due to randomness increases. Okay, due to randomness increases. So why denaturation of egg, entropy more means randomness increases. Next, third one, stretching of rubber. Another example. Stretching of rubber, entropy decreases. Why stretching of rubber entropy decreases means disorderness decreases. From original rubber to stretching of rubber, disorderness decreases. That's why here disorderness decreases. Some examples. So you also follow different examples. Exam not only given these examples. Okay. So you have studied some more examples in your reference books. Okay. Some more examples also you have to collect. Okay. This is about the randomness or disorderness applications. How can entropy increases or decreases? surrounding. Inverse equal to system plus surrounding. For system really system observed heat energy observed by the system. That means system to surrounding heat energy supply one way, then heat energy supplied from surrounding to system another way. Already knows. So now for system minus Q reversible by T. Okay. Now heat energy released from system to surrounding. Next. For surrounding, heat energy released from system to surrounding means system got a negative heat energy. Surrounding accepting heat energy now. That's why for surrounding plus Q reversible by T. Total universe equal to total universe del S equal to minus Q reversible by T plus not needed directly plus Q reversible by T. So minus plus cancel. That means equal to 0. That means in total reversible, complete means total reversible nature, entropy in total, otherwise instead of complete you take total. So total reversible nature del S equal to 0. So listen again, heat energy from system to surrounding, that's why for system minus Q. Then so here system lose the heat energy, that's why minus Q. Here surrounding absorb the heat energy, that's why plus Q. Total inverse equal to system plus surrounding, that's why del S equal to Q reversible by T plus Q reversible by T. Minus plus cancel 0. So total reversible nature del S equal to 0. Del S equal to 0. Okay. Next one. Entropy in total irreversible nature. Entropy in total irreversible nature. So here T1 greater than T2. Okay, that means so first temperature more than second temperature. Same here inverse equal to system plus surrounding. Same take up for system equal to minus Q reversible by T. Next for surrounding plus Q reversible by T. Okay, here two temperatures different, irreversible two temperature different, because in reversible nature initial to final to initial, that's why temperatures are same. But irreversible, it cannot be reversed in any state of the system, that's why two temperatures are different. So for surrounding, total universe equal to total process equal to minus Q reversible by T plus Q reversible by T. Okay, now this is T1, this is T2. So here we taking T1 greater than T2. If temperature 1 more than temperature 2, if we taking initial temperature more than final temperature, that's why first one T1, second one T2. This is class we have to go Gibbs energy.